Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so my name is Aaron Smith, and it's my pleasure to introduce Shinpei Kato. So Shinpei is a recent graduate of Keio University, and he's now a visiting researcher at Carnegie Mellon University, where you're working with Raj, can't say his last name.
Raj Kumar.
Raj Kumar, yeah. So can you give us an interesting talk today, and just turn it over to you.
Thanks for introduction. So my name is Shinpei Kato. I am currently officially a postdoc at the University of Tokyo, but I am visiting Carnegie Mellon University. So first of all, I would like to thank Aaron for giving me this opportunity. So today I'm talking about system software support for GPU accelerated applications. So before the talk, let me introduce myself briefly. So I received PhD at Keio University in 2008, and there, so my PhD thesis is real-time scheduling. And after that, I moved to University of Tokyo, and there I was working on the operating system support for interactive supercomputing. Then, from the fall last year, I joined CMU, and there I'm working on operating systems for autonomous driving. So my research interests are in the areas of real-time systems. And particularly, I am interested in operating systems design and implementation, including CPU scheduling, GPU scheduling, network scheduling, and so on. And application domains I have been working on are, for instance, humanoid, or multimedia, and autonomous driving, but not limited to these domains. So I'll show you some movie regarding the humanoid, which I have been involved in development. Sorry, the subtitle is written in Japanese, but the humanoid is a real-time application. And every action begins with vision-based perception. So every time it has to work, it has to recognize something. So in this case, the humanoid has to recognize what it has to interact with, or who it has to interact with. And this is a huge application, which is composed of very timing-critical applications. And of course, very fine-grained control needs to be provided as well. So this is a collaborative work with Keio University, the University of Tokyo, and ICE. ICE is a research institute in Japan. So I have been working in this project where I used to develop the operating systems for the humanoids. Okay. So let me introduce another movie, which is about autonomous driving that I am working on now. The autonomous driving is very similar to humanoids in many senses because both humanoid and autonomous driving applications are categorized into robots. So actually, I am working with Professor Raj Kumar, and he was the technical lead in the autonomous driving project supported by GM. So the team won the DARPA challenge in 2007. So this car is called BOSS. And so we actually improving the functionality of this autonomous driving car, even for now. So you can see that, of course, it is unmanned car. So it can drive itself, deciding where to go, what to do. And for instance, if the car encounters some white line, it has to stop. And it has to check if no other cars are coming in front. Okay, let's just. The movie is a little bit long, so I just cut here. But basically, what I have been working in is something like this. So robot, autonomous driving, and so on. The real-time interactive applications. But from my viewpoint, these applications, these systems look nice, but it's not fast enough for practical use. for instance, humanoid just walks very slowly, it's good for experimental evaluation or something. But if you want to use the humanoid in dynamic environments like the real world, I think it wouldn't work. The same thing can apply to the autonomous driving. The car can drive itself, but if we put the car on the traffic in the real world, I think it wouldn't work. That's because so these autonomous systems have to take care of many processings in real time, for instance, vision-based perception, or localization, mapping, matching, motion planning, object tracking, learning control, and so on. So these real-time applications have to go in parallel every time. So the figure is just a simulation. The simulation is still slow. If the simulation is slow, we cannot translate the applications into the real world. So this case, so you can see, can show the movie again. Oops, I can see. So I don't know if you can see from there, but the car is deciding where to go. So the white object is another car, so it has to avoid to hit. So it decides, it seeks for the line where the car can drive on. So as we just looked, these applications are very heavy. So definitely we need some computing, the scalability in the computing power. But let me show another movie where we can see more easily the computing power is definitely lack for the up-to-date multimedia applications. So this is a collaborative work with Keio University and Toshiba's Corporation. The product is actually shipped, as also known as Toshiba's Cell TV. So you can see the interface is nice, but if you carefully look at the screen, only the one TV show, which is focused, can play. But if you want to have better interfaces, people may think if all TV shows on the screen can play, then that's better, which is, I believe, is a better interface. But with the current, today's CPUs, we couldn't do that. So instead, we just gave up showing all the TV in parallel. Instead, we decided to play only the one TV show, which is focused. So today, I'm going to talk about GPUs, which probably can scale up the computing power. But before that, just let me give you some ideas what we really need for real-time computing. Because even though you have a strong computing platform, if you do not care about real-time, then we cannot build up the applications. So if you want to make realize of real-time computing, basically, you require to have timeliness. And timeliness is basically provided by meeting deadlines, which are directly related to safety or quality and interactivity. And to meet deadlines, you need to prioritize tasks correctly. And also, you need to isolate tasks strictly. But prioritization and isolation are not easy stuff to realize. So it may be a little bit boring for you, but it is important to see how, for instance, scheduling problems affect the application. So let's consider 3 periodic tasks on 2 processors. So this is a quite simple example. And we assume that these tasks are scheduled based on just deadlines. So if we have 3 tasks to schedule, if you think of media players, so media players, basically frames arrives almost periodically. And these frames want to be processed within its period. So here, because we only have 2 processors, probably task 1 and task 2 would be scheduled first because they have earlier deadlines than task 3. Then after the frame, execution of task 1 and task 2 complete, then task 3 can resume. Here, because we have 2 processors, probably one of the processors left idle because we only have 1 task to execute here. Then the task 1 and task 2 arrive for the next frames, they preempt task 3 because they have earlier deadlines than task 3. By the same token, task 3 would resume when the task 1 and the task 2 complete. But if task 3 has a long execution time, it would miss a deadline, even though we have many idle times remain. If you think of a little bit better scheduling, such a timing violation can be easily avoided. So for instance, I introduced deadline and slack-driven scheduling, which changed the prioritization policy a little bit, but this a little change significantly improves the system's performance or system's schedulability. So here, as the deadline-driven scheduling, we basically execute the tasks based on deadlines. But we can provide some functionality to look ahead the scheduling only one step next scheduling point. And in that case, we can probably predict which task may miss a deadline. And if we detect some task to have a deadline miss, like this case, the task 3 would have a deadline miss if it is not scheduled immediately. Then we can simply preferentially schedule the task 3 first, regardless of the priorities or regardless of the deadlines. So what I want to say here is prioritization is basically very important in timing critical systems. So that's what I'm going to talk about. So if we shift to more larger scale of computing platforms like GPU, even though we have a strong computing power, if you do not have any scheduling scheduling algorithms which can take out the system to be schedulable, you never get the interactive real-time systems to be nice. So here, this is just an example how effective these scheduling policies are. So I tested. Oh, sorry. Get some dirty, but OK. So I used today's CPU to test if some scheduling problems can affect the system performance. And in that case, we imitated the prototype of the Toshiba's TV. So we simultaneously play 6 high-definition videos on the screen. And the graph shows the frame rates of the mainly focused avatar's TV. And if you do not care about, if you just simply use the deadline-based scheduling, you actually see the frame rates drop significantly. But if you use a little better scheduling algorithm, you can basically improve the frame rates. Sorry, this machine is actually not the same one as I made a PowerPoint. But so if you also take care of memory management or networking, then you can even make the system better, which I have demonstrated in my previous work. But so if you focus on the test platform, it's just 6 videos on today's Intel CPUs, which means, to me, CPU performance doesn't scale well. So even though we provide a good scheduling algorithm, if you play 7 or 8 videos simultaneously, then your systems eventually get messed up. And such a performance scalability issue would apply more critically if you think of further futuristic applications like 3D online game, computer vision, 3D interface, and so on. And these application domains actually is the one that I am very interested in my future work. So I would like to provide the solution how we can scale up the performance for these real-time systems. So the question that I am trying to address in my research is how can we support data or compute-intensive application real-time computing? Well, I believe that most of data-intensive real-time computing or data-intensive applications would benefit from the computing power of hardware accelerators. So there are mainly two types of hardware accelerators as long as I know. So one is GPU, like the one developed by NVIDIA. And the other type of hardware accelerator is a so-called many-core that the Intel is trying to push into the market. Well, they are both categorized into hardware accelerators, but they have different architectures. For instance, GPU generally integrates so many simple processing cores. And in case of NVIDIA GeForce GTX 480, it includes more than 400 cores on a chip. On the other hand, in the case of Intel's solution, they embed only 32 cores, but these 32 cores are based on Intel's architecture, so which means each single processing core is much more powerful than the NVIDIA's GPUs. So they adopt different solutions. So because they have different architectures, I believe we should have different software architectures as well. And as the technology leads today, we actually run the operating system on the CPU, and from the CPU, we control the GPU. On the other hand, I have read some couple of articles that propose it would be better to run the operating systems on each core in case of Intel's many-core architectures. Actually, I'm not quite sure how we can provide a solution for many-core because the many-core has not yet been in the market. That's why, in my research, I am strictly focusing on the GPU for now. So today's talk, let me focus on the GPU. So GPU is originally developed for graphics processing. But at the same time, if you have a program language support, it can also be used for general purpose processing. And this is a simple performance comparison between representative Intel CPUs and NVIDIA's GPUs. And if you look at the performance per watt, NVIDIA's GPU is actually more than 5 times faster than Intel's CPU. And if you don't care the performance per watt, instead, if you only care the performance, then NVIDIA's GPU is more than 10 times faster than Intel's CPU. So yes, we have quite strong computer architectures to scale up the performance. But the question here is, what about system software challenges for these hardware accelerators? And the key observation, which I have got from my experiments, is multitasking problem. So GPU is used to be used for accelerating only one primary application, like 3D game. But if you think of more complex applications like autonomous driving or humanoids, then you want to run the multiple programs at the same time, and each of which needs to have some timeliness. But what happens if, so I ran some experiments where I try to execute a 3D game where other graphics applications are also running together. And here, I used 2 different system software, GPU drivers, device drivers. One is NVIDIA's official driver. And the other is an open source GPU driver called Nuvo. And I also used 2 different GPUs. One is a low-end GeForce, and the other is a high-end GTX. And in all setups, in all these scenarios, I actually encounter a significant performance loss on the 3D game if some other applications are running background. So the blue box indicates the performance of the 3D game when it runs with low workload widget application. And red box indicates the frame rates of the three. Yes?
Just a very brief overview of how the driver affects the scheduling. Is the driver basically injecting low-level yielding commands into the stream that's going to the GPU, and
yes,
one driver is doing that differently than the other? Is that?
The scheduling policy between, these two drivers used almost the same scheduling policy, just send the GPU commands in their arrival orders. But what I'm saying here is this is the problem. That's why I want to provide a different solution. So particularly, if 3D game runs with high workload graphics application here, I call it graphics bomb, then the performance, the frame rates of the 3D game drops even below 1/10 of the case where the 3D game is running standalone. So actually, I have identified why such a performance penalty, performance loss, was posed. So the first problem which I have found is priorities are not effective at all on the GPU because of the drivers. The second problem which I have identified so far is that there are non-preemptive regions on the GPU. So these two factors actually disturb the 3D game or multitasking execution system to have timeliness for the overall applications. Here, I can show some simple example how priorities or non-preemptive region affect the system's responsiveness on the GPU. So assume that a high priority task like 3D game arrives first. Because the GPU is idle here, so it can send the GPU commands to the GPU, and the GPU commands can execute on the GPU. But if other activities also send the GPU commands to the GPU, while some other GPU command is executing on the GPU, they simply blocked. And after the preceding GPU command completes, then these two pending GPU commands will execute. And regardless of priorities, regardless of any arrival patterns, GPU commands are just executed in their arrival orders if you just use the open source driver or NVIDIA's driver. Here you can see that priority inversions is likely to happen. So for instance, here, a low priority pink task is executed before the high priority blue task. And the same is true for the rest of the execution. And as a result, a high priority task can be blocked by a low priority task. And this blocking time is actually not bounded at all. If, for instance, a graphics bomb keeps sending a huge size of graphics command, then a high priority task can be blocked for a long interval.
Couldn't you just have some scheduling software sitting between those that you submit your task to, and it knows the priorities?
That's what I'm going to talk about. OK. So here, I made some abstraction, quite simple abstraction. But if you have a closer look at the parallel GPU processing, if you use the NVIDIA's old architectures, they only allow one channel, one GPU context to execute at the same time. That's why I can abstract the execution of GPU like a single-threaded execution. But if you use the NVIDIA's new Fermi architectures, it can allow multiple channels, multiple contexts to execute at the same time, like here. So therefore, the Fermi would improve the system throughput eventually. However, the problem is fundamentally the same. So you can see that still a high priority blue task is affected by a low priority pink task because we don't have any scheduling nice scheduling algorithm in the GPU driver. So I'm going to talk about how we can insert a scheduling algorithm into the GPU driver. But before that, let me give you some concept of GPU driver model. Because as long as I know, NVIDIA has not yet released any detailed documentation to open. You guys, because you are working at MSL, so you may have some collaboration and you may have some documentations. But in general, we don't know at all what NVIDIA's driver or what GPU software is doing. So that's why I joined open source project, where we keep hacking the GPU, for instance, keep sending some commands to the GPU, and just see the reaction. And the project has lasted for 3 or 4 years. And finally, we got the precise GPU driver model. So we actually identified what the NVIDIA's driver is doing. So that's what I'm going to introduce here. So applications call API functions provided by library. And the library converts the API functions to GPU-specific commands and send them to the user space GPU driver. Okay. And in the user space, this procedure is just repeated. And at some point, the user space GPU driver sends the system call to the kernel space GPU driver. And this kernel space GPU driver then submits the commands. But here, the command submission is not that the kernel space GPU driver submits. Oh, sorry. Yeah. So here, when the library converts the GPU-specific command to the GPU-specific command and send them to the user space GPU driver, it writes into the memory mapped space in the kernel. So the space may be on the system RAM, or the space may be on the video RAM. That's what is decided by the operating system. But the GPU command is written to the memory space, which is mapped from kernel space to the user space. So anyway, then when the user space GPU driver sends a system call to the kernel space GPU driver, it writes some packets to another space of memory in the kernel space, which is called command buffer. So command buffer is a ring buffer, and it keeps write a packet into this ring buffer. And each packet is composed of buffer size and address offset that points to the actual place of GPU commands. Then GPU reads just these packets. So this ring buffer is accessible to the GPU. So the GPU can read the packets, then fetches the actual GPU command groups to the internal GPU engines. So the first problem, which I introduced before, so these GPU command groups. So GPU command groups is a set of GPU commands. So these GPU command groups are just executed in their arrival orders. Plus, these GPU command groups are non-preemptive because they are a set of atomic execution. So under these constraints, but still we have to provide some solutions to improve the timeliness for data-intensive real-time computing. Therefore, we proposed some GPU scheduler. So our GPU scheduler operates in the kernel space, coordinating with the original kernel space GPU driver. So we don't need any changes to the user space. So the GPU command groups are just generated as before, same as before. However, when the GPU command groups enters the GPU command submission interface in the kernel space GPU driver, the command group is hooked by a GPU command scheduler provided by our GPU scheduler and enqueued. And instead, the GPU command scheduler dispatches the GPU command group issued by the most important or high priority task. Then, once the GPU command group is submitted by a GPU command scheduler, it just goes through the same path as before and finally goes to the GPU. Here, when each GPU command completes, our GPU scheduler set up the GPU to generate an interrupt from the GPU to the CPU. And this interrupt is relayed to the GPU command scheduler so that we can dispatch the next task. So basically, what we are doing is it's to provide the mechanism that that enables the GPU drivers to have the scheduler as the operating system CPU scheduler does. So we queue GPU command groups in a dispatch. So the scheduling policy is quite simple. So when the GPU is not idle, just GPU command groups are queued. And when GPU gets idle, GPU command groups are dispatched based on priorities. If the GPU command groups are executed under this scheduling policy, you can provide a priority-based executions. So here, I'll show some example. So there are two tasks as before with different priorities. And let's assume that a high priority task arrives first, and it submits the GPU command group first. So because GPU is not idle at this time, so any GPU command groups are queued when when a GPU driver tries to submit. Even though the high priority task arrives, it is queued. And because we set up the GPU to generate an interrupt when the preceding GPU command groups completes, the GPU scheduler can invoke when the preceding GPU command group completes. Here, because the GPU scheduler knows which command groups are enqueued, so now when the GPU gets idle, so the GPU scheduler dispatches the GPU command group based on the priority. In that case, a high priority task can go to the GPU first. Then, when a high priority task completes on the GPU, a low priority task finally can go to the GPU. If you see here, you can see that the task executions on the GPU are correctly prioritized. So now we could provide the prioritization for the GPU, but prioritization itself is just to prioritize the tasks. If some malicious task keeps executing on the GPU, it can mess up the GPU resource again. So that's why we need to have some reservation strategy for the GPU as well. So the GPU resource reservation that we have proposed is to regulate the GPU resource usage. And we can simply specify the capacity which is allowed to be spent on a GPU in a period P for each task. So if you imagine the Linux control group, you can specify the execution time and the period that are assigned to the tasks using the Linux control group. So let's assume there are two tasks again, and we assign the capacity C to one of the tasks. And when the system begins, the execution budget is initialized to C for each task. So in that case, in this case, we assume that the blue task has the budget C and a period P. And this budget is decreased by the same amount of the time that is spent by this blue task on the GPU. The scheduling is still the same as the one I just introduced in the previous slide. So it is executed based on the priority. However, so because, as I said, each GPU command group is non-preemptive. So if the remaining execution budget is not enough to service the next GPU command group, then the budget can be negative if we just let the GPU command group to go to the GPU. But that's fine. Our solution, we have two solutions here. The first solution, it says soft. So we allow the budget to be negative. However, once it gets negative, we do not allowed the task to go to the GPU, even though it has a higher priority than others, because the budget is now negative. And this budget is replenished at every period p. So at some point, at some later point of time, the budget is replenished by the amount of c. Now, the high priority task, high priority blue task can go to the GPU finally, eventually. So there is another reservation policy that we have proposed is a hard. The hard reservation policy is more strict in the sense that we can regulate the GPU resource more strictly at the expense of course, incurring overhead. So in the hard reservation, every time the task goes to the GPU, we check, we predict how much time the task would spend on the GPU. Due to time constraint, I do not explain how we predict the execution time of the GPU command group, but the GPU command group execution time can be predicted based on some history. So because if you imagine like GPU computing programs or OpenGL programs, they use APIs. And the APIs, each API generates a very similar sequence of GPU commands. So if we keep the histories of the previous GPU command groups, we can somehow learn what combination of GPU commands consume how much GPU time. So we keep the history, and based on the history, we predict the GPU command execution time. And if the GPU command group execution would not cause the execution budget to be negative, we let him go. But however, when we predict the execution time of the task on the GPU, then if we predict that the execution budget would be negative, we do not allow him to go because it may overload the GPU. So instead, a low priority task can go to the GPU. And like the soft GPU reservation just I introduced in the previous slide, when the execution budget is replenished by amount of C, this high priority blue task would be able to eventually go to the GPU, unless it is predicted that the execution budget is not going to be a negative value. So here, I tested some performance interference to see how well 3D games are prioritized over and isolated from competing graphics bomb. So as we saw in the previous slide, if we do not provide any timing support, the performance of 3D games is just messed up. But if you put high priority, high GPU priority to a 3D game, you can significantly improve the frame rates of 3D game. And further, if you use priority and GPU hard reservation, soft reservation, then you can moreover improve the frame rates of 3D games because this case, we limit the GPU resource usage of background graphics BOM to be 10%. And if you further use hard reservation, so soft reservation, the GPU graphics BOM still could spend more than 10% of GPU resource because it's soft. But if you use hard reservation, it never allows the graphics BOM to spend the execution budget more than that it reserved, so it can provide a slightly better performance. So if we want to use the GPU for data-intensive real-time computing, this property is very important because you can guarantee that your important programs running on the GPU would not get affected by other background jobs or other competing jobs. here I can show how well frame rates of 3D game can be and 3D widget are regulated. So we don't care how much time the graphics BOM spend, but we still care some widget applications. Like if you imagine the 3D desktops, then you probably want to run your 3D game, but you still want to have some browser plugins or desktop components based on the 3D graphics that they still use the GPU as well. So in that case, you can regulate how much GPU resource can be used by each application. So this case, so we set up the GPU resource usage so that the GPU utilization becomes totally 100%. So for instance, if the 3D game is assigned 10% of GPU resource, the other competing 3D widget is assigned 90% of GPU resource. And if we scale the size of reservation, then almost the 3D games, the frame rates of 3D game increase proportionally. So which means the reservation is actually working. And same is true for the other 3D widget. So if the size of reservation is decreased, then the frame rates of the 3D widget is also decreased almost proportionally. So these 3D games are basically exhaustive. So they try to execute as fast as possible. But we have different type of applications, in particular for real-time systems like media player or any humanoids or autonomous driving applications. They usually arrive periodically, and they want to be processed within their period. So if we use the media player for evaluation, it actually matches for what we want to achieve. So here, media player is basically want to keep its frame rate to be at 24, because this is the standard definition for playing movie. And if we use priority support and the reservation support for the movie player, so we can tightly guarantee that the end player can consume at the desired rate. But if you do not have priority or reservation support, and if you just use the NVIDIA's GPU driver or open source GPU driver, then your end player, media player gets affected and messed up. So here, by these experiments, we showed how important to provide the priority and reservation solutions for the GPU. There are some work in progress. So we're working on finer-grained GPU resource management or high-throughput GPU data communication. So let me show you how we try to improve the granularity of resource management for the GPU. So the GPU is actually a very complicated architecture. So GPU internally contains many engines. I don't know how many engines actually that today's GPUs provide, but at least we know that today's GPU, like the one provided by NVIDIA, they include graphics engine, power management engine, and the code encryption decryption engine, and the context channel engine, and the video decoding engine, and so on. There are many other engines inside the GPU, but we do not fully understand how many and what type of engines are provided by GPU, because NVIDIA doesn't release the documentations open. However, we know that every existing engine on the GPU has a microcontroller. So microcontroller is like a CPU, small CPU. It has own instruction set. It has code and data sections where some small programs can execute. And it also provides interrupt or exception mechanisms. So we can basically run a complicated program if the program size is small. So the idea here is, why don't we install some embedded OS inside the GPU so that we can provide finer-grained resource management. So let me show you how we actually install the operating systems to the GPU. So you first write the operating system as you like by using the instruction sets provided by microcontroller like this. And you can simply write this binary code into the I/O port, which is defined by the GPU itself. So in my GTX 480 graphics card has the I/O port at 0x blah blah blah. So if you write a code into this I/O port, you can basically install your own OS on the GPU. And once you write this binary code to the I/O port before you use the GPU, your operating system will be activated when you use the GPU. And if we have own operating systems on the GPU, we can provide finer-grained, for instance, scheduling. So the previous example, I showed that we can somehow prioritize and isolate the tasks executing on the GPU, but because each GPU command group is non-preemptive. So for instance, this case, even though we have a priority-driven GPU scheduler at the device driver layer, if the high priority task arrives when some low priority task is already executing on the GPU, it has to wait until the preceding GPU command group completes on the GPU because this is non-preemptive. So if here, in this scenario, if a high priority task has an earlier deadline, then the high priority task may eventually miss the deadline, even though we have a priority-driven scheduler at device driver level. So what we are trying to do is to coordinate with a microcontroller. So every time a task arrives and tries to submit the GPU commands to the GPU, it can send some command packet to the microcontroller through I/O through a specific communication port. So there is some specific communication port which is mapped by GPU microcontroller itself to the system memory. So we can write some packet to this area. Then the microcontroller can read which command is sent by system CPU side. So every time a task arrives and tries to submit a GPU command, we can notify the microcontroller of the arrival of important task. Then we know that from the microcontroller, we can save and load the GPU contexts like CPU. So we can basically provide a context switch mechanism if you have own operating system on the GPU.
How expensive that is?
That's not expensive at all because video memory and the GPU is connected by very fast memory bus, GDDR5. It's about 100 gigabytes per second. So from the microcontroller, you can just, as the CPU does, save all the context to the video memory, and you can load another context to the GPU. Okay, so so in such a case, if you switch to the high priority task quickly, then you have more chance to avoid deadline misses. And also, we know that the scaling voltage and frequency is also possible for the GPU. So as we already know, we have many algorithms for dynamic voltage and frequency scaling. So we can apply these algorithms to the GPU as well. So when some task arrives and tries to submit the GPU commands to the GPU, and if we have a low workload, then probably we can scale down the voltage and the frequency of the GPU to save the energy, to save the power. And combining with context switch, we can probably provide real-time power saving and thermal control at the same time. And we already have some experimental results, but they are not organized yet, so I cannot show on the slide here. But we actually tested these technologies are now possible for the GPU. right? So we actually are trying to use this fine-grained GPU resource management for our project. It's running in Japan. It's a green exascale computing project. It's a collaborative work with University of Tokyo and IX. IX is also a research institute in Japan. So it's an exascale supercomputer. We're developing an exascale computer called K. So of course, its main goal is to realize the post-petascale computing, but we're also trying to use the supercomputer for more interactive and real-time use. For instance, in Japan, we have many environmental problems like tsunami or downpour and earthquake. So we can probably use the supercomputer or data center to provide environmental forecasting mechanism. Well, to develop such supercomputer, of course, the GPU is one of the best suited approaches because its computing scalability is, for now, much greater than the CPU. So we have planned to develop a GPU cluster. But however, making GPU cluster has many potential problems, for instance, particularly in data communication. So if you want to build up the GPU cluster, you probably have a system like this. So each node has a GPU and a CPU. They are connected by a PCI interface. And the current state of the art in PCI technology is just around 4 to 8 gigabytes per second. On the other hand, GPU is connected with video memory by GDDR5, which is around 100 gigabytes per second. And also, you can scale the network as well. If you use InfiniBand and combine many InfiniBand links in parallel, then you can actually even achieve the communication throughput over 100 gigabytes per second. So, which means we have a bottleneck on the PCI communication. So there are some technologies that support GPU data communication, like NVIDIA and Mellanox have a solution called GPU Direct, but it's still not fast enough from my viewpoint. So here the example shows some problematic GPU communication. So if we receive data from the network, and this data needs to be processed on a GPU, but because we have to copy the data to the place where the GPU can access. And the current solution is that so the data is copied to main memory first because the NIC driver has a receive buffer on the main memory. But GPU generally wants the data in video memory, so it has to copy the data to the video memory to process. So there is at least one copy to be posed. And before the NVIDIA and the Mellanox solution, there is another copy from the main memory to the main memory because GPU still has to have the data in the main memory where it can access. But the NIC driver doesn't know where in the main memory the GPU can access. So there was another copy from main memory to main memory. And NVIDIA and Mellanox have some collaborative work to reduce this unnecessary copy. Then they reported that 40% of throughput improvement was provided. But still, memory-to-memory copy is posed at every data communication. So we try to even remove this copy. And so we are studying why we needed this additional copy at every data communication. And we, well, simply identified that that's because NIC driver and the GPU driver are developed independently. So that's why they cannot communicate with each other. So what we are doing is, so when we receive data from the network, what we want to do is to copy to video memory directly. Because if we can do this, then the data communication throughput will be improved significantly. So the problem is how we can do this. So basically, there are 3 address spaces that relate to the GPU communication. So one is I/O address space, which is used by PCI communication. And there is main memory space and also video memory space. And the GPU drivers basically map the I/O address space to its own space. For instance, the NVIDIA's official GPU driver maps a part of PCI space to its memory mapped registers. So because we map these I/O memory mapped registers to the PCI space, we can control the GPU from CPU. And also, NVIDIA's driver maps the GPU processing data to the PCI region. So the CPU can write the GPU commands to this space. Then finally, this GPU processing data can be copied to the video memory. So there is a mapping problem. So you can map the PCI region either main memory or video memory. And NVIDIA's solution is they map the I/O registers because they do not access these registers frequently. So they can map to the main memory, which it takes longer time to access. But it's OK because they do not access to the I/O registers frequently. But on the other hand, GPU processing data need to be on video memory because they are used very frequently. So every time the GPU tries to compute something, they have to access this data. So because we can map the PCI region like this, we can do that when we receive the data from network. We can have a receive buffer not only on the main memory, but we can point to the PCI I/O address space as a receive buffer. So because NIC driver has a direct memory access controller, and we can tell the address for the receive buffer by the PCI address space. Then every time data is coming, NIC driver just writes the data to this space, which means if we write the data to this space, because this space is mapped to the video memory, it can directly copy to the video memory. So because actually InfiniBand is quite complex communication standard, so we didn't try with the InfiniBand yet, but we actually evidenced that we can do this direct GPU data communication with Ethernet. So, which means we believe that we can do the same, make the same mechanism with using more faster InfiniBand.
Code the packets, because you need to know which packets should go to this.
Oh, that's a protocol problem. So what we showed here is we can directly copy the data from main memory, driver space to the video memory space. But yes, we need some protocol stack implementation specific for the GPU data communication. Or I can skip this. So there is another project running in parallel. So we can apply the same idea to different domains. For instance, 3D video. So 3D video is 3D pictures that can be seen from any directions. So 3D TV, you can just see the object from the front. But 3D video, you can see it from any directions. And we are collaborating with CMU's Robotics Institute and also Kyoto University. Yeah, we can skip this. So basically, 3D video streaming, we need to set up camera, and we need to capture the video from multiple viewpoints. Then we need to reconstruct the object, and we visualize the object. Finally, we can send it to the stream. So this needs to be done in real time. So it's, again, very heavy computational application. And this CMU group is trying to use a GPU. But they first tried to use the CPU, but they couldn't make everything in real time. So they were forced to have offline calculation because the computing power was lack. So they're now trying to use the GPU, but still we have a problem in communicating between the GPU nodes. So we now having collaborative work. So that's more, I guess, significant to have a direct communication, because when you receive the data from camera, we can here directly copy the data to video memory. Then we can again directly copy to the NIC when the data needs to go to the stream. So if we do not have a direct communication mechanism, you have to copy to the main memory first. Then from main memory, you have to copy data to the video memory. Again, when you want to send the data to network, you have to copy to the main memory first. Yes. OK. So we believe this direct communication mechanism is more significant for these 3D video streaming applications. But still, we have scheduling and memory management problems, or we need to specify some driver APIs, because if we have heuristic implementations, then each driver needs to have different, different implementation. But we want to provide some driver API specification for GPU direct communication, so that we can easily develop GPU or I/O drivers. OK, so the memory management is also problematic, because video memory is a limited space. So if all video memory is already used, you cannot basically allocate data. So imagine the CUDA programming. If you try to malloc the data more than the size of video memory, the malloc just fails. So the first idea that we should provide at least is we need to some swapping mechanism between main memory and the video memory, so that we can use more and larger space of memory. But still, we need to copy the data to evict the data from main memory to from the video memory to main memory. So the overhead is imposed on the application. So what we are trying to do is we always try to keep some space not used. So because we keep the space left unused, when the application wants to allocate the data on the video memory, it can easily, of course, allocate the data. And because GPU execution is independent from the CPU execution, so we can make another space by evicting some data from video memory to main memory while GPU is executing some commands. So which means we can hide the performance overhead imposed on data copy. So summary, so in this research, we showed that prioritization and isolation are possible for GPU accelerated applications. And the challenging issues, what we are trying to address for now is a fine-grained GPU resource management that can provide, I think, better timeliness for data-intensive real-time computing. And also, we think it's possible to make realize of high-throughput GPU data communication. But of course, GPU is not much known. The GPU architecture is not much known because NVIDIA does not have any available open source documentation. So we need more in-depth investigation for the GPU, and as well as more generic many architectures that we believe the market would have in the future. In the future vision, so Google is actually developing autonomous cars. So Google actually took some people from CMU and Stanford, and they made their own development team for the autonomous driving. And I found some interesting article. So the first article, which I thought very interesting, is so Google's CEO said, so it's a bug. The cars were invented before the computers. So your car basically should drive itself because it just makes sense. And I quite agree with him because if we have computing technologies before the car was developed, then we could have more intelligent cars by now. And the other article which I found from the Google's source is, so Sebastian is a Stanford professor, but he's a distinguished Google engineer. So he said autonomous driving, its technologies are all made possible by Google's data center, which can process the enormous amounts of information gathered by their cars. So which means they're trying to make use of their data center's technology and embed autonomous computing, autonomous driving computing. So because I also have the same background, so my project running in Japan, it is for exascale computing. And at the same time, I also have another project that I am involved in at CMU is about autonomous driving. So it is going to be very interesting to combine these two different domains of research. So for instance, you can provide whole areas of the United States to each automated car so that they can drive from eastern coast to western coast. But these communication and data processing need to be done in real time. So it's a challenging issue, which I am very interested in. And eventually, maybe we can develop some intelligent autonomous driving car. Yeah, that's all. Thanks.
So I have one question about the scheduler that you embedded into the video driver. Is that available for download?
Yes. Technically, yes, but we have submitted the idea to some conference, which is double-blind. So I guess we can make it open after we get.
Yeah, if your paper gets in, you can
Yes.
get it on board.
Yeah, but that's completely, organized open source project, which everyone can download from our website.
Okay. Is it part of the Nouveau driver that you were talking about?
Yes, but Nouveau is an open source project, but they do not care about real time. But instead, we forked another project from Nouveau where we take care of more interactive or real-time use. And this another project, actually the project is very willing to use the solution for real-time computing. So hopefully by next year we can integrate our solution to the open source project.
So when you were talking about the hardware resource management,
Yes.
There is some overhead associated with that, right? Because you need to gather the statistics about the previous GPU commands,
Yes.
and then you need to predict, right? And did you try to estimate, like, in terms of either latency or post CPU usage, like how much it is?
Actually, hard reservation is time consuming. It's not that much time consuming for practical use, but of course it imposes computational overhead. But
In terms of GPU operations, does it drop total, like let's say time bomb plus the 3D game, kind of total operations submitted?
The primary applications is not affected, but because the prediction is going on, for instance, graphics bomb. So the performance of a graphics bomb can be, decreased by predicting the commands. But so you don't want to use the hard reservation, for instance, for widget application. But widget application is by nature not supposed to affect the primary application so much, so we can use instead soft reservation. But graphics bomb or any other unknown malicious applications, probably we can use hard reservation. And once we verify that the application is not malicious, then we can switch to soft or something. Like we can change the scheduling or reservation policy on demand. But if you have any chance for the application being malicious, then you want to use the hard reservation so that we can strictly limit the GPU's resource usage of the application.
I was thinking, you have this interrupt.
Yes.
And I have this dislike for interrupts for some reason. I feel that they're expensive.
Okay.
Since you're already doing some prediction, could you just do something to get rid of the interrupt using the prediction?
Yes, but what happens if the prediction is not precise? Yes. It can be non-precise, I mean imprecise.
I'm just wondering if that saves you anything or
Yeah,
provides
could
you
be.
more slack in your schedule.
Yes, yes, possible.
When exactly interrupt fires? When the buffer is fully empty or when it has space for next command? Then, excuse me? When interrupt fires? When the ring buffer is fully empty or when it has space for the one command?
No, it's kind of tricky. So there is a GPU command that generates the interrupt. So we on purpose adds a set of actually 3 commands at the end of each GPU command group, so every time, yeah, controllable.
Well, any more questions? You can always chat afterwards. Okay.
Okay. Thank you.